of Dortmund University of Technology in Germany. So his research interests are in remote sensing, photogrammetry, which is extracting 3D info from photographs and using it in the application of it in the field of planetary science and the industrial domain. So Professor Kirsten did his master's from Würzburg University in 1996. And then he did his PhD in computer science from Bonn University in 2000.
Pardon?
Deep computer audio.
Pardon.
No audio. Yeah.
No idea. Oh. No audio. No audio. That is output. But you mean the microphone? No, the microphone seems to work. There is no sound anymore. That's off. So the computer's own sound is off. Oh. Now something is happening. Okay, that seems to work now. Okay.
Yeah, sorry for the glitch.
No problem. Am I audible?
Okay?
Am I audible now? Okay,
Yes, yes.
Okay, that's good.
So yeah, so today's topic is telescope imaging, polarimetry of atmosphere-less solar system body. Yeah, Professor, yeah, you can go ahead.
Yeah. Thank you very much for the introduction. Thank you very much for the invitation to speak here today. Yeah, my talk will be about telescopic imaging polarimetry of atmosphereless solar system bodies. In our group, we are mainly focused on planetary remote sensing. And one might think, what does that have to do with it? But it has, because also telescopic imaging is a sort of remote sensing, just a bit more remote than usual with satellites or aircraft. And I will look at quite different species of atmosphereless solar system bodies. Namely, yeah, no, I have to use this here. No, that doesn't work. Simply can't.
Now can you try?
Okay. Okay, good. So what is imaging polarimetry? Imaging polarimetry is a well-known but often neglected, I tend to say, method for examining the small-scale structure of cosmic dust. Mostly the structure, the morphology, and to some extent a little bit also the composition, but to a lesser extent. For composition, one usually employs spectroscopy. And cosmic dust means a lot of things. For example, it's simply interplanetary or interstellar dust, but also dust in comets, which is to some extent similar to interplanetary dust. And also, which is also dust, the surface regolith of airless celestial bodies, such as asteroid, our moon, the planet Mercury, the moons of Mars. And so this is all cosmic dust. And there is no unified understanding of the scattering behavior of cosmic dust yet, although all the time when we look at solar system bodies or even exoplanets, we look at some kind of cometary, of some kind of cosmic dust. At least when the exoplanets are also atmosphereless, and that exists. Comets have a low density of dust in their coma and tail, and due to that low density, the good thing is that one doesn't have to care for multiple scattering. So we can use classical scattering theory. You have sunlight coming in to the comet, one scattering process, and then light goes off to Earth. That's good, because it makes the whole thing numerically treatable to some extent under the single scattering approximation. I will go into more detail later. Asteroids, Moon, Mercury. So when I say asteroids and the Moon, I also mean Mercury and Mars moons, and maybe also Io with the silicate surface. There is no commonly accepted numerical model, physical model available for dust on asteroid and the Moon surface due to the high physical complexity of the scattering processes involved. That's the regolith on the Moon is much more densely packed, and then the dust in comets, there is clearly multiple scattering, and there is no physical model yet that can be used to explain polarimetric observations of the Moon and similar bodies. In this talk, I will present recent observations and, if available, modeling studies of the polarization behavior of comets, or especially one comet and the Moon. And then I will also point out a little bit of comparison between lunar and asteroid polarization. The comet and lunar polarization observations were all conducted by myself and collaborators, all of them from India. And asteroid polarization data were taken from the literature that I've never done by myself. So these are just some comets. Recently appeared comets of different kinds, just to illustrate how different they may be. So you see, they were all taken with very moderately sized telescopes and cooled CMOS camera, RGB color camera. And you can see, for example, that this comet here, C2025K1, that looks very much yellow, just like the very bright comet Tsukinshan Atlas that was visible at the end of last year. I think I must change the shape of this to laser pointer. Yeah, that's what I want. And here you can see, and you can even see here that these images are very recent, a bit more than a week. I took them from Germany, and you can see how the nucleus of this comet is breaking up into 3 pieces. That can also have a big influence on the dust properties, because dust is released from the interior of the comet's nucleus. This is the comet C2025A6 Lemon. This image taken beginning of October, that image taken 6 weeks later by early November. And you see, morphologically, totally different. Here you have a green coma whose emission is governed by the emission of maybe several molecules, especially the C2 double carbon molecule. And its emission line is in the green domain of the visible spectrum. And 6 weeks later, just before perihelion, we observed several dust outbreaks and dust events, and there has been, and then a really big dust tail, the broad one, has developed. The whole comet appears also yellowish, and whereas in the early image there was just a straight a straight gas tail, which is white, so not red. And if you want, you might be able to see a little bit of a dust tail here, but that's very tenuous still, whereas here it's really very bright. So that these are changes that may occur during just a few weeks. Here, this comet is much fainter. It was very much at the limit of the equipment I dispose of in Germany. that is C2025R2 Swan. The remarkable thing about this comet is that it doesn't really have a tail. It's, yes? Yes? Ah, okay. What the difference is, a gas tail looks more or less exactly like this. It is straight, narrow and straight, because it's driven away from the nucleus by the solar wind, and there is hardly any gravitational. So the gravitational effect is very small in comparison to the radiation pressure regarding the gas molecules. Whereas once you have dust particles, depending on their size, there is a gravitational effect and radiation pressure effect, and both might counteract each other, and then you get this broadened fan-like shape, which can even be curved. So then you have at least two forces at work, and that's how one can distinguish them. And here, this comet here, Swan, only has a coma, which is green again in the C2 emission, and here this not so well visible comet. This is a periodical comet, which is known since early 19th century, discovered by a German astronomer, Friedrich Wilhelm Olbers. This comet returns every 60-something years, and you have a dust tail here, but also this slightly greenish glowing coma. So there is a mixture of both. That is actually quite interesting. So I'm talking about emission lines and everything, although I don't show spectra, so because I don't have them, and they are in the literature for some comets, sometimes not. This is poor man's spectroscopy with an RGB camera, but that's totally sufficient to distinguish between the different kinds of constituents. And if we want to go for the dust in the comet, and there is a gas component, the usual way of removing the gas component is to insert something like a Johnson-Cousins R filter, or some orange filter at least, that cuts off all emissions shortward of 550 nanometer. Then all the major emissions are absorbed and only the dust remains, basically. Okay, and here are values from the literature. How do cometary polarization phase curves, that means degree of linear polarization plotted against phase angle, how do they look like? This is taken from the famous book chapter by Kiselyev et al. 2015, who in turn collected data from the literature. And you can see that there is one class of comets, the high P-max comets, with visual maximum polarization values of up to maybe 25% or something. They mostly look the same. And these outliers here are said to be due to a breakup of the nucleus, just like the one I showed you, but another comet. And here's another class of more variable, low P-max comets, which has maximum polarization degrees between 7 and also 25. Or does it really belong to, let's say, less than 20%. So 25% is definitely not low P-max. Anyway, so the distinction is not totally clear. There is no sharp boundary. What is known today, but that's not what I want to focus on. What is known today is simply that high maximum polarization and low, so high polarization occurs for dynamically new comets that are for the first time transecting the inner solar system, whereas low P-max comets occurs for comets that are periodical and have been various times near the sun already. And apparently that leads to some differences in the structure of the cometary dust, which is partially known, partially unknown yet. So there's a lot of ongoing research of explaining those measurements with physical simulations, numerical physical simulations. For our own cometary measurements, we used a sort of innovative measurement technique which stems from the lunar data which we acquired previously. But since I'm beginning with comets here, I'm explaining that first. It's a camera, it's an off-the-shelf industrial polarization camera, where, as you can see here, each pixel of the sensor is doped by a little polarizer, which transmits different polarization direction. And each 2x2 environment acquires 4 polarization directions of more or less the same region of the image. That is not so good for stars, because stars are point-shaped and one has to blur them in order to distribute the light sufficiently. But it's good for extended objects like comets, like the moon, anything that is resolved by the optical system. And the sensor looks like this. It's that tiny, so you can put it simply in the pocket and take it elsewhere, which I did. So I took it also to India, to Mount Abu so far, and also here I will show you. So that's a very practical thing. And I learned recently that nowadays there also exists, this is an uncooled camera, but there exists now also a cooled version of that camera. So it will make that special Sony sensor even more practicable to be used in astronomical environments. Pardon? It's four directions. Yes, yes. Pardon? Yes, with a single detector and simultaneously. It just leads to a reduction of the resolution by a factor of 2, because each 2x2 pixel cell gives you the polarization parameters for one location. But that's it. The price that you pay is the lower resolution. But okay, so it's a 5 megapixel sensor, and then it comes down to a 1.2 megapixel sensor in resolution, and all the polarimetric parameters are also in the. That's really good, I think. So we could make very reasonable measurements with it. The good thing is the acquisition of all polarization directions is simultaneous. So if there is a little bit of fog or some atmospheric things that one doesn't see during the measurements, it doesn't matter, because the absorption is the same for all polarization directions as they are acquired simultaneously. That is extremely valuable if you want to take measurements in a country like Germany, where you never have really clear sky. So if you want to wait until there is really a sky like here all day, clear, no single cloud, nothing, ideal photometric conditions, we don't have that. So, and especially near the horizon, where the comets usually are, even less. And the parameters that we get is mean flux F, just the intensity, then the degree of linear polarization, P, and the position angle of linear polarization, which we call W. And the optical system might look really small, 150 millimeter aperture, 600 millimeter focal length. But nevertheless, with the camera, we get a pixel scale of 2.4 arc seconds per pixel. That is totally fine, given that at least at my location in Germany, the seeing is usually like that. So don't need really more. And if it's a large comet, then it's totally fine. We could also use a slightly larger. We are planning to use the Mount Abu 430 centimeter aperture Ritchey-Chrétien telescope for such purposes as well. But even such a small and portable, so that you can go where there is good weather, a telescope is absolutely useful, as you will see. And as good physicists, or physicists trying to be good, we do an error analysis, of course. So with such a sensor, because that will be the first question when you do something new with a new sensor that is different from existing sensors, So we simulated the response of the sensor for certain, just SNR values of the underlying images. And the results, though, are applicable to any DOLP measurements, including those obtained with the traditional point or imaging polarimeters that you usually use. So, but we have, of course, sometimes not so good, not so high SNR, especially when we try to image the comet's tail. And that is the actual goal, because not many people have done that for some reason, and we did it. And others have done it before with limited success and extremely bad data quality in most cases. But here we achieved some good measurements, at least, not all of them. And if you have a low SNR like 10, here the red curve, you will see that a true DOLP of 0.1 of 10% translates into a measured average DOLP of 20%, just because you have noise, and then you always fit that cosine curve into the noisy data, and then you will always get a certain amplitude of that cosine curve, even when there is no polarization at all. As you can see here, if the polarization is near zero, you still measure something like 0.2. That's inevitable. If you have such noisy data, then you will fit a cosine into the noise. And this is what happens here. It's okay that happens with any kind of polarization measurement. That's by no means unique to this kind of setup, but one simply has to know it. Just the cooled traditional polarimeters, they have a better SNR, a higher SNR, and you can see when the SNR reaches 1000, this is already a lot, that's 60 dB, then you can very well measure DOLPs below 1%. Even 300 is already able to do so. And on top of that systematic error, there come some statistical errors, of course, but they can value for the tail only anyway, then this is also fine. Okay, then let's look at a typical measurement. Oh, it's actually a good measurement. That was the comet Zukin-Chan Atlas on October 23. This is the intensity in 16-bit digital numbers, scaled to between 0 and 1. You can see the very brightest part is saturated because we wanted to measure the tail. How did we obtain these images? There is one trick behind it as well. We didn't take one exposure, we took hundreds of exposures of no more than 4 seconds exposure time each, because more is not allowed by that specific camera. I hope the cooled camera will allow for more, the cooled version, but this one doesn't. So we took hundreds and hundreds of images and stacked them. And so that's a method well known from planetary imaging, for example, and for comets it also works. Then we simply did what I explained and obtained this kind of DOLP image. Here, this is the AOLP, but that's not so important. There are some fluctuations, but it's not clear if they are real, because it's just about a few degrees. It's not the absolute position angle, it's just the deviation from the mean. And here the DOLP is more important, and you can see that towards the coma it becomes lower. And we get a rather unique and relatively universal relation here of DOLP versus intensity. And so for moderate intensities, you have more or less linear behavior in that log-log plot with a negative slope. And for very low intensities, this curve has a saturation, or this relation shows a saturation. That means, and for very high intensities, there's also some kind of saturation effect. That's why we fitted a hyperbolic tangent or sigmoid function to that relation, and by extrapolating to infinite plus infinite values, we get the coma DOLP, the brightest part, and by extrapolating to minus infinity values, we obtain the DOLP of the faintest part of that of the tail. And here, this is what such a typical measurement actually looks like. So here, this is the polarizer orientation at 0, 45, 145, and 90 degrees. And you can clearly see that the tail length changes. And that simply means the tail has a really strong polarization, as we can see in the image in the upper middle. Whereas, yeah, the coma also changes its brightness, but not so much. So polarization will be fainter. These are the observations that we made for that comet, for coma and tail. So there was a South Korean group that developed a new polarimeter and used it with a 50 centimeter telescope, I think, who measured the coma as well, and their values are very similar. That was, first of all, very reassuring for us. So they also, Lee et al., I don't know, that doesn't help much. Lee et al. 2025. When you search for Lee et al. 2025, you will, of course, find many papers, but I forgot to mention that paper exactly, but these are our values anyway, but they are very close to what we found in the literature. When you look at that curve here, the estimated maximum value is more than 0.3, so that's a very high Pmax comet, even more Pmax than the high Pmax comets of Kiselev, which is probably due to the fact that this comet is a dynamically new comet which transacts the solar system for the first time. So red and purple is coma, blue and cyan is tail, and you see that the tail has a consistently higher polarization than the coma. We also have tail measurements at, here the polarization curve always has a zero crossing at a value of about a bit less than 20 degrees. Here it's something, 20.5 degrees, which is a very typical value. And but according to the error measurements, the error estimation that I just showed you, these measurements here with something like minus 10%, and at the same time an SNR of 10, that is probably just an upper limit, but not a really accurate value. So we cannot measure the weak negative polarization of that comet. It's not doable. For the coma, it worked in contrast, and we even had support from our colleagues at Mount Abu. The black crosses are measurements by Goldi Ahuja, PhD student of Sashi Kiran Ganesh, who measured that same comet at similar phase angles from Mount Abu, from the 1.3 meter reflector. And that's all quite well consistent, I would say, which was also reassuring. Okay, and then the question is, how do we explain those observations? Doing observations is nice, but one wants to know what is behind them. And the usual approach is polarimetric modeling of cometary dust, and there are basically two main types of dust that are used in simulations. One is fractal aggregates. They consist of little spherical particles that are glued to each other and form fractal aggregates, which are very porous. And with the number of these so-called monomers, those are the little spheres, they are much smaller than a micrometer, order of magnitude 100 nanometer, maybe a bit more. By changing this number of monomers in the number n, you can also change the particle size. So with 512 monomers, you get these large, complicated particles. And by changing the fractal dimension, which is between 1.6 and 2.2 here, and I cut it off for some reason, you can also influence the particle shape. So here you have more compact particles, here you have more porous particles, depending on the fractal dimension. And down here, is another particle type that's from the article by Halder and Ganesh. So that's from computations made by Pritish Halder, who has been working at PRL, and he designed these, or he constructed these called agglomerated debris particles. They are less porous, and their polarization behavior has to be computed with a different method, which is called a discrete dipole approximation. I don't want to go into details here. So these are just two methods well described in the literature. And when we look at real images of cometary dust, this one comes from comet 67P Churyumov-Gerasimenko. This image was taken by the atomic force microscope, MIDAS, on board the Rosetta spacecraft. Yeah, you see that you have actually this kind of monomer structures here. It's enhanced a bit by these cyan circles. And what also comes out is that such particles also exist. So what we did is we assumed a mixture of them. So one shouldn't simply stick to one. First, we only tried with this kind of particles, but our simulations didn't fit with the observations. Then Halder, Pritish Halder joined us, and he contributed computations, simulations for these agglomerate debris particles. And this is now, again, our measurements, but not with fitted curves, but with, so not with the phenomenological fit like in the previous version, but with model results. So what we can say is we get a good model fit for the coma. That looks really nice. But of course, when we go towards the tail, we have some constraints. So we cannot simply say the composition of the tail is completely different from that of the coma, because the tail particles are assumed or likely to come from the coma. So they are just driven out of the coma into the tail by the solar radiation pressure. So why should they change their composition? We used the same composition. That's a more or less not yet well-established problem in comet simulations. For only a coma DOLP phase curve, you always find physical parameters that explain it. There are many physical parameters in the model, so that makes it easy to find some solution, which also says the problem is probably highly ambiguous. But if you have a tail and have certain constraints on composition, and also morphology, so the morphology of the tail particles, okay, might differ from the coma particle morphology, but not totally. And so we had some constraints. And the main parameter which we changed between coma and tail was the relation between fractal aggregates and agglomerate debris particles. So here, for the coma, it's 50-50, and the black tail curve is also 50-50. We can say, oh yeah, that might fit to the measurements, but not really so well. Especially here, that's not really nice. So what did we do? We added more agglomerate debris. And we got here 25 to 72. We got the blue curve. That's already quite okay. And if we use only agglomerate debris, then yeah, maybe a little bit too much regarding the, it might be a little bit to the right, but on the other hand, the measurements of the tail due to the low SNR are uncertain, so we can't say too much. We can say likely there is an excess of agglomerate debris in the tail relative to the coma, but even that we cannot finally conclude. So we just say, okay, it might be possible. Pardon?
On the measurement of the
answer,
DOLP.
yeah, that's what I try to explain here. There is a systematic error, but on top of the systematic error,
What I am asking is that because there are three models may be on the similar uncertainty.
That's right. So the models were not fitted to the. So we just guessed some parameters and looked if they fit. So we didn't systematically optimize the models, because that would have been computationally too demanding. Because already one model run took several days.
Oh.
That's the problem. So the uncertainty is about plus, I would say, plus minus 0.1. Let's be a bit pessimistic.
0.01.
No, plus minus 0. Yes, plus minus 10%.
10%.
Yeah, maybe 5%. If I were optimistic, I would say 5%, but I'm not. So I say 10%. That's yeah. And there is a power law size distribution of the particle. That's the usual assumption, and also fits with Rosetta measurements. And for that power law size distribution, we have an exponent of n equal 2 in the coma. That fits well. That it's also very well established in the literature, and it fits here as well. And in the tail, we found something like 5, which is a much higher tendency towards small particles. It's okay. And additionally, we need a constraint that in the coma, there are no particles smaller than 0.6 micrometer. That's a cutoff that was sort of adjusted so that it fits. Okay, but that is explainable because such large particles here, if they are glued to each other by frozen volatiles after emerging from the nucleus and after staying some time around the nucleus and then being torn into the tail by the solar radiation pressure, the volatiles will sublimate, and then such large agglomerate particles or fractal aggregates might decay into smaller ones, and they might even decay into their individual tiny 100 nanometer size monomers. And that's what they probably even do, because we need such, because we do need such very small particles of near the Rayleigh scattering limit in order to explain the observations. And this is expressed by that. So then we include also those very small fractal aggregates or also agglomerate debris particles into the simulations, and they are needed to explain that high degree of polarization. So in principle, these are actually the first systematic tail measurements made so far for a comet, at least which are accompanied by a simulation and in combination with the coma. Our paper is still is in the second review round, I can say, so I hope we are close to it. So it's submitted to ANA, and I hope it will appear soon. So let's see, one never knows. But that review was really hard. Okay, that's what I wanted to show you about comets. And interestingly, nearly all of these measurements were taken with that 150 to 600 millimeter telescope. So also these telescopes are really useful in that case. And with a cooled camera of that kind, even much fainter comets will become accessible. So with a cooled RGB camera and such a telescope, one can easily go down to comet magnitudes of 15. That's possible. So the good thing is, at least in Germany, we don't have observatories with telescopes of a meter size or half a meter size or so, because where should you put them? 80% of the time there will be rain. And if you want to track comets over a longer period of time in order to cover that broad range of phase angles, in principle, you need to go where there is good weather. So pack everything into the car and go. And that's the plan. So we are about to apply funding for a project that will do exactly that. So with portable equipment, go towards some location nearby where there is good weather and maybe not so much light pollution as elsewhere, because in our region we cannot do it. From one single location. That's absolutely impossible. And the big observatories, they will not say, okay, we grant you observation time for 1 day every 3 weeks for the next 6 months or so. That's rather unlikely. So I think we found the gap for using small telescopes here. Okay, then let's go towards the moon. And I will first talk about the positive polarization of the moon. That is the polarization that occurs around 90 degrees phase angle. This is a very historical set of measurements made by Liu in 1929. That comes from this hint is hidden. That comes from the Hapke textbook of light scattering and emission treatment. So you can see here the lunar polarization. This is the positive polarization branch. This is the negative polarization branch, and I will discuss one after the other rather quickly. So what we do is measuring the DOLP in 5 spectral bands, just standard Johnson-Cousins UV-VRI. That has hardly ever been done. Don't ask me why. And since then we get 5-dimensional spectra. So if we don't have a broad phase angle coverage, but just look at one single phase angle, we nevertheless have 5-dimensional spectra, and that's already a bit difficult to interpret. So we use a principal component analysis to reduce the dimension to 3 in order to be able to produce nice color images, and that is then also very convenient for clustering and prototypical wavelength-dependent polarization detect behavior extraction. That's what we want to do. So this is here. This is the instrument with which these data were acquired. That's from a paper that we published in 2024 in A&A. No, in the astrophysical, in the astronomical journal. Sorry, astronomical journal. Here, these are the Dibyendo Misra and Sachna Satyan, 2 PhD students of my colleague Megha Bhatt at PRL in Ahmedabad, who visited our group at that time. And this is a 20 centimeter, 1200 millimeter Newton reflector with a stationary setup. And that is quite suitable for taking images of the moon, because we don't need a larger aperture, because the seeing for this aerial object is never better than the resolution of the instrument anyway. Usually it's much worse. Okay, so this is a region in Western Oceanus Procellarum on the moon with the craters Aristarchus, Kepler, and the famous structure Reiner Gamma, which is a magnetic anomaly and a so-called swirl. Here you see the degree of linear polarization. Here you see the angle of linear polarization, but the amplitude is again very low, so we didn't really interpret anything into it. I'm just showing the data, but it's not clear if this is real or if it's due to crosstalk between the pixels or whatever. So that's difficult to tell. This is an ensemble of several pyroclastic deposits in the middle of the lunar near side, Mare Vaporum and Sinus Estuum. Here is the the DOLP image, and here is the angle image. And this is the crater Atlas, more towards the limb, the northeastern limb of the lunar disk. This is the DOLP image, and this is the angle image. And one thing we can see immediately here is that there is apparently an inverse correlation between intensity, this is just intensity, and the DOLP. So what is dark in the upper image is bright in the lower image. That is quite clear. And that's what also was no real surprise, because that effect is known as the Umov law. Umov established that law, or found that law in 1909, I think. His paper was published in German language. And so that the DOLP decreases with increasing albedo. And Umov himself said that it's an inversely linear correlation. That's strictly not true. So if you plot into a double logarithmic plot, then you will get different kinds of slopes, which are always negative, but not always exactly -1. That doesn't matter. It's still known as the Umov law. It's just a power law, not an anti-proportionality. And the classical explanation here, because we see, and if we do that, we see deviations. So here, for example, you have a little cluster. Here we have another little cluster. And the classical explanation by Spuratov et al., actually the only person and his group, the only persons on this planet who ever really looked into very deeply into lunar polarization during the last decades, until the Ukrainian war made their work impossible, because they are from Sharkov Observatory. They explained that in 1992 by a difference in grain size, because they found a similar effect in the laboratory for lunar grainy samples of different sizes. But more recent work by Zubko et al., another Ukrainian, also coming from that same group, he states that this direct effect, there may be a correlation. Obviously, there is a correlation between the deviation from that blue line and the grain size, but that can also be just a correlation, but no causal relationship. Because the regolith grain size, the regolith grains are relatively large, tens of micrometer, much larger than optical wavelengths. So actually, one wouldn't expect too much of an effect here. Okay, so it could also be that maybe there are structures on the big grains, small structures, that are differently pronounced, and then they might change the polarization. That's, for example, possible. But actually, Zubko shows that the structures needed to change the polarization need to be somewhere close to the wavelength, which means less than a micrometer in the optical domain. Anyway, pardon?
Minutes for the talk.
5 more minutes for the talk.
Okay. I understand. Okay, so this is here, this is this grain size, as we can see. If it's a grain size, otherwise we just interpret it as a deviation from the Umov law without really knowing what physical effect is behind it. We need to see. So you can see these pyroclastic deposits show some deviations also here. The Rainer gamma swirl and also crater rays on the moon do that. And we can see here, this is the result of clustering, and the result here, these are the resulting prototypical DOLP spectra. At least this helps to boil down the information into a small number of representative spectra. Okay, other measurements were made last year together with my colleague Professor Deepak Dhingra from IIT Kanpur. You can see us there at the telescope here at Aries. the 104 centimeter telescope. And here's our very little full moon refractor. And on that, the data are incredibly difficult to analyze, or time consuming, not difficult, just time consuming, because it's actually terabytes of data that are acquired during a few sessions. So this is what the crater atlas looks like through the Zampunanan telescope. These are some color-enhanced IVU composites, so not RGB, but IVU of crater Copernicus, the Gruithuisen domes, the complete lunar disk. And this is a putative swirl next to the crater Wolf in Mare Nubium, where we can also see a distinct deviation from the Umov law. So that's something which is not yet explained, because we don't know what is the property that causes these changes, but this is very much similar to the much more well-known Einer gamma sphere. And now just a little view at negative polarization. Negative polarization looks at this small part of the polarization curves. We will again use principal component and clustering. I will not explain again. This is with the same camera. This was done in collaboration with Dr. Mega Bhatt at PRL. This is Mount Abu. This is our instrument. This is the camera at the instrument, so always the same camera. We also adapted that same tiny camera to the huge telescope here. And we specifically look at this area at the pyroclastics again, because one of Mega's PhD student, Didiendo Misra, is working on pyroclastic deposits. This is again an IVU composite we obtained in that way, where you can see the pyroclastics as really dark and purplish material. Purplish because they are probably titanium rich. These are the parameters. You can see correlations with mare areas, highland areas, and pyroclastics, especially here in the V-band slope, but also here. This is the absolute minimum polarization, and so you also get some structures. Then you can again do a PCA over all wavelength channels, which shows very nicely here these bright areas as the pyroclastic deposits, and you can cluster them here in different clusters again, and you differentiate between different landforms. That makes absolutely sense. And here are again the prototypical spectra. The very high polarization values here in the U band, I don't really believe them anymore, simply because that might also be due to the low signal to noise ratio in the U band. Moon is very dim in U, sensor is very unsensitive in U, that leads to low SNR. So simply ignore these U values. They are, so I wouldn't believe them. But this is all work in progress, so it's not yet published in a journal, but just on a conference. And of course, we have one region, namely the crater atlas, where we analyze the whole curve with 6, which we describe by 6 parameters. We use this trigonometric model for that, which we also used for the comet, where I didn't mention it. The target area is this is atlas again. This is Chandrayaan-1 moon mineralogy mapper reflectance. We worked a lot on those data sets, and this is our calibrated reflectance. And then we can also, we can visualize our PCA results. Here you see this intense block. This is a pyroclastic deposit. That one again, 2, the northern one. The crater has 2 pyroclastic deposits. That works very nicely. And here are actually the prototypical spectra of the parameters that we derived. And what do these letters mean? The letters mean the ranges for asteroids of different types. So we have S-type, M-type, and C-type asteroids. C-types are the chondritic asteroids. And what you can see is there is always one parameter where, so here we can, okay, sorry, this dark blue curve, that's just shadow in the image, so that should be ignored. The other ones here, they concentrate around the asteroid data. Most asteroid data are in the visual or red domain. Here you see that only the C-type asteroids correspond with the lunar data. Here in that parameter only the S-type, and in that parameter here only the C and M type. So there seems to be a consistent difference between moon and asteroids. It's not that we can say, okay, we simply look at lunar data and then we look at asteroid data, then we find the most similar lunar data, and then the asteroid surface will be similar to that specific lunar terrain. That was the original idea we had, but it's not feasible because asteroids are systematically different. It's a pity, but well, it's like this. So these are just some data from the famous Benjoya article, which show small phase angle measurements of asteroids of different types. I just reproduced here the data from the literature. These are not our measurements. And this is a diagram where you can see this, the absolute minimum, absolute value of the minimum polarization. This is the phase angle at which the minimum occurs. And here you can see lunar data of lunar terrains in different spectral bands. Here this is U, so U has a very high P min, so maybe ignore, better ignore, that's unreliable. But anyway, that doesn't change anything here. We can draw a clear separation line between the different types of asteroids or typical asteroids. We didn't extract all of them from the literature, but just a representative set. And here we are still able to show that there is no overlap in this parameter space, which means asteroids are systematically different. If we understood the reason for the polarimetric behavior, we could even say why, but that's work in progress. Okay, in summary, imaging polarimetry yields a unique view on cometary dust, definitely, and also on the solid surfaces of atmosphereless solar system bodies, such as Moon. And the physical modeling of the polarization behavior of cometary dust particles yields information about size distribution, morphology, to some extent also composition. Composition in the sense silicate versus carbon, not really which specific mineral. These are, and these dust grains are assumed to be very similar to the primordial matter out of which the sun and the planets and their moons forms. So that makes those measurements important. Otherwise, you could also say, why do I care about cometary dust? It's just some kind of object, and it's not interesting. It is interesting because our solar system was formed out of such matter, and that's why actually Scheiferli and I, we are here because we are observing, or we have been observing, the interstellar comet 3I Atlas, which comes from another star from another planetary system, and is just transecting our solar system and will then disappear into space forever and will never return anytime again. So the question is, if we try to analyze that comet in the same way, will its dust, which is the original building blocks of that remote parent solar system, will the properties be similar, or will it be completely different? So is the home of that comet built from different building blocks or from similar building blocks? At the moment, the indications are that it's not totally different, which is also an important insight. That just means that star formation in our vicinity of the galaxy at least took place under similar conditions. And this comet is a sample that can be accessed directly from Earth. Cannot yet, usually you cannot yet assess the dust properties of exocomets. So that's not yet possible. There is no commonly accepted physical model of planetary regolith surfaces yet, but at least I think I've shown that we can use polarization parameters to segment and classify surface units and identify them with geological units even. That's what Megabat's PhD students are doing. And that segmenting is not according to composition or something, but probably according to some structural regolith surfaces to obtain an improved physical understanding to relate better the observational data to these physical or structural regolith parameters. I think laboratory experiments will be good. In our lab, we can't really do them, or it's difficult. We try at the moment a little bit, but there are institutions that are much better equipped for such studies, for example, like PRL. They are building up something like that, and we'll see if we learn more about that. Yeah, and I leave it at that. Thank you very much. Any questions? We're happy to answer them.
Nice talk. So you said that you analyzed the impact craters on Moon, and they were very different from asteroids.
Very different, I wouldn't say, but at least different. Yes, that's right.
So isn't impact craters on Moon were made due to the asteroids? So what actually makes this difference?
Of course, there are impacts on the Moon, and they make impact craters. That's right. Usually not much of the impacting asteroid survives. So usually the impacting asteroid evaporates, and that only causes the big explosion that forms the crater. That's the commonly accepted mechanism. So and also on asteroids you have impact from other asteroids as well. And nevertheless, the differences remain. But there's one important difference. I was wondering at first too, why is it so totally different? Asteroids have many asteroids have extremely low gravity. So the Moon has 1/6 of a g, and of course then due to that the regolith is compacted. And on asteroids that doesn't happen. So if there are impacts and some particles fall back on the surface, many won't because the escape velocity is low. But if the particles that fall back on the surface, that will only form some fluffy, very porous grainy surface, and that is exactly what the spacecraft data tell us, and that might have something to do with these systematic differences in polarimetric properties.
Thanks.
Again, my question is that how many craters have been studied polarimetrically, and whether they have a similar property or the different property? Is there any relations between them?
That depends on about which resolution you're talking about. So the Skuratov group has made global studies of the lunar polarization with resolutions of maybe 2 kilometers, but only in the red domain and maybe the green domain, not in 5-band polarimetry. And fresh impact craters show, that's also clear from our results, fresh impact craters show similar polarimetric properties. For example, they also show a similar deviation from the Umov law, which one might interpret as a larger grain size or different small-scale roughness of particles or whatever. So just say structural difference. So fresh impact craters have a rather unique signature that is easy to recognize. And then larger craters often have no signature at all because they have already been space weathered to the degree that, just let me see here, for example, that crater Wolf in Mare Nubium. Here you have no deviation from the Umov law. That's totally unconspicuous because that crater is really old. And yeah, then all the structural differences have already been equilibrated by something like yeah, micrometeoroid impact, for example, and so-called impact gardening. On the other hand, you see this bright spot here. That is, if I'm not wrong, that is a small impact here crater, and here those ones too. Here, this one you can see is a bright spot. That was near full moon, so bright spots at full moon are fresh impact craters, and they appear as anomalies in that anomalies in the deviation from the Umhoff law. So there are unique behaviors of specific types of craters, especially fresh craters. But older craters don't have that much of a anomaly, because due to hundreds of millions of years of micrometeoroid impact gardening, space weathering by solar wind particles, and so on.
Maybe. So I have like in your polarization camera, because you have these 2x2 pixels where you measure this IQ UV parameters. So do you also get some kind of polarization crosstalk between the pixels? And if yes, then how do you like remove that in the analysis?
I hope not. So it's very difficult to verify, because usually one would say, look at the standard star, but then the standard star is point-like, and then there will be definitely crosstalk. That's at least you will one part of the PSF will fall on this pixel, the other part on that pixel. They will be acquired under different polarizer directions, and that's deadly. So I don't know. We have not been able to measure the crosstalk due to we don't know how, and we don't have the equipment. But I can now say, when I look into the literature, of our Korean colleagues who measured the coma of the same comet in the same phase angle range in the same period of time, with a very sophisticated classical imaging polarimeter, then I would say, and their measurements are nearly identical to ours, within a % of DOLP, I would say. I concluded from that our measurement can't be that wrong. But you are right, there can be crosstalk, but it's apparently not that bad. And why do the South Koreans do that? Because they have an instrument on the Korean Lunar Pathfinder orbiter where they do global spacecraft-based polarimetric measurements. That's why they do that. I was very surprised to see those data. But that is the systematic comparison that we have at the moment.
So I have one question. Like,
yes?
You showed your degree of linear polarization depends on signal to noise ratio, no?
Yes.
Very much.
Yes.
And for the dust case, you showed how the signal varies. So what is the value in the moon, like for signal?
The signal to noise ratio.
Yeah.
That depends very much on the spectral band. But in R and I and G, we can easily get something between 300 and 1000, rather 1000.
So actually very good in some
It's
sense.
very good. In B and U, it's maybe less than 100, so it's not so nice anymore.
And second thing is, like, for the comet, the polarization is higher by a factor of 10 compared to the moon.
Not always. So moon can also reach 20% easily.
Okay. So it is maybe the reason because of the dust is less in the moon compared to the comet.
Pardon?
The degree of polarization is lower in the moon because of the low dust in the moon, or?
It's not even really lower. So if we say comet typical is 20%, and we look at our DOLP maps here, then we see that it also goes up to 0 to 20% and more in the I band here in that case. So dark surfaces then have similar maximum DOLP values as comets, and comets have a lot of carbonaceous materials which are dark. So the albedo of comets is comparable with the albedo of the darkest areas on the moon. And if you compare that, the polarization curves are actually quite similar, at least for the cometary coma. For the tail, you're right. Tail is much more polarized, but that has to do with the much higher fraction of very small particles that with sizes close to the Rayleigh limit.
Okay.
So
So
is
let us,
it-
okay.
Just one question. Is it,
Okay.
is it easy that to differentiate polarization due to the reflection or the dust particle in case of the comet?
Reflection,
Yeah, that is albedo and all.
pardon?
Albedo.
Albedo polarization due
Albedo.
to, yeah.
In the comet, we actually don't see the nucleus. It's so small, it's at most 20 kilometers, it's absolutely not resolved. So all the light that we see in the comet comes from the tiny dust particles, but not from the nucleus. I think we wouldn't, with that setup, one wouldn't even be, if there was only the nucleus, if it was an asteroid of the same size at the same position, one wouldn't be able to see it with this setup.
Okay, let us thank the speaker for the interesting talk.
Thank you.
Thanks.